So, what did we talk about last time? We just got started with some dynamics stuff, right? So we talked about continuous time dynamics. And we talked about manipulator equation, right? And remember, like, I'm never going to make you like derive this stuff for any kind of system in the class. That's not what we're about. I just want you to know what these things look like, in particular because if you use any kind of robotics toolbox that does dynamics for you, it's going to spit out the manipulator stuff. So you're going to kind of need to know what that is and how to work with it at least. Cool. So that's that. And oh yeah, and then we talked about linear systems at the very end last time. These things are, as I mentioned last time, like the bread and butter of control. They show up everywhere. So you really should embrace, the AX plus BU thing. We're going to see it a lot, and it's super important, super useful. Okay, so kind of building on that, today we're going to talk about, started getting into analyzing dynamical systems. And this sort of is going to carry us into some control stuff. Super important. So the first topic is going to be to talk about equilibria. So equilibrium points of dynamical systems. And then we're going to talk a little bit about stability of those equilibria, which is a huge control topic, right? Typically we want to stabilize systems so they don't crash, fall over, blow up on us, that kind of thing. So we're going to talk about stability a little bit. And then we're going to start talking about, and we'll see how timing goes, discretization, time discretization of these dynamics. So far we talked about continuous ODEs, F equals MA stuff. That's great. You can do some analysis with that, but pretty soon you kind of run up against the fact that generally speaking, we don't know how to solve nonlinear differential equations. Life is nonlinear and hard. So we pretty soon want to start doing stuff in computers. So this is really getting at how you solve ODEs in a computer, how you simulate dynamics in a computer, how you, that kind of thing. So that's what we're going to start talking about pretty soon. So we'll call it discrete time dynamics and simulation. And just as a kind of heads up thing, this class is, very kind of practical computation sort of focused. So we're pretty much after this initial little foray and looking at continuous time stuff. Everything in the class will be in discrete time and very kind of computation focused and how to implement stuff. So we're not really going to do much in continuous time. So if you haven't seen ODEs before and they make you slightly uncomfortable, don't worry. Pretty much not going to use them. It's all good. Okay, so that's what we're doing. Any other questions about anything? Everyone happy? Excellent. Okay, here we go. So we talked a whole bunch last time about dynamics. We talked about this idea of x dot equals f of xu being this prototypical, most generic form of dynamics. And so remember that. We're going to now talk about what an equilibrium of a dynamical system is. And intuitively, everyone knows what this is. Can someone give me a quick intuitive definition of an equilibrium point? You've seen this before? Anybody thoughts? Yeah. Yeah, so it's basically a point at which the system is at rest, where it's not going to move, right? Makes sense? And so mathematically speaking, that's, we'll write that down quick, a point where the system will sort of remain at rest. And mathematically, right, if we were talking ODEs, that's where x dot, right, the time derivative is 0, where it's going to stay still and not move. So if we're talking xu, this whole thing's got to be 0. So from an algebraic perspective, an equilibrium point is a root, a 0 of the dynamics. Make sense? All right. So now we're going to look at this for everyone's favorite nonlinear system, pendulum again. So just recall from last time, we're not going to do it again, right? We did these dynamics, you know, little F equals MA stuff, but this is what this looks like for the pendulum. Minus G over L sine theta. And so for now, we're just going to look at the uncontrolled stuff real quick. And so no tau, no U, no torque on the pendulum. And what we're looking for are the points where this thing is 0. So can anyone tell me intuitively where this is going to be? Yeah, so hanging down, right? And then there's one up here too, where if you could theoretically like perfectly balance it, right, it would stay up there too, right? Okay, so that sort of happens when theta dot equals 0, obviously, no velocity, and then theta, and really what we're talking about are the zeros of that sign downstairs, right? We got to zero that out. So it's where sine theta equals 0. So that happens at 0, pi, et cetera, right? And that's getting back to the thing we said last time where, you know, the state space is really cylinder, the configuration space really a circle, not really the real line. So, you know, it's got 0 pi, you know, 3 pi, 4 pi, blah, 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 but those are all the same because it all wraps around. Okay, so we've got, we'll just draw this real quick. Pendulum up, this is theta equals pi, and we got pendulum down, theta equals 0. Cool. Okay, so that's clear to everybody. That's what we're doing. So now we're going to take this and like think about it a little bit, and we're going to write down our first baby control problem. And this is kind of, you know, the flavor of stuff that control theory deals with. So the first question I'm going to ask you is, can I use, so we do have a control input, right? We have this torque. Can I use control to move the equilibria? What do you guys think? So let's try that. So let's say, for example, I want to make an equilibrium at pi over 2. Let's try it. So this would mean I can plug in theta equals pi over 2. We still want theta dot to be 0. But now I've got minus G over L sine pi over 2. And now I'll put the control back in there. And I've got the 1 over ml squared u. And I want this whole thing to equal 0. So I solved the root finding problem, that bottom equation in particular, right? I want to make that bottom line equal 0. And I have the u there to help me do it. So if I kind of just set that whole bottom line to 0, I've got 1 over ml squared u equals G over L sine pi over 2. And kind of just thinking about this real quick, you end up with u equals mgl. There's a couple ways to think about this. One is just you're basically doing gravity compensation, right? You're basically just setting that torque equal to mg, right? Such that you're canceling out gravity. There's a really common thing on robot manipulators, right? We often see arms often come with a gravity compensation controller. It's exactly what they're doing. They're figuring out the u such that the gravity torque goes away. You can also do this, right, for any other theta in principle. And in general, what you're going to get is a root finding problem in U. So you're going to get something like, you know, say I want my equilibrium point to be some x star, you're going to get this problem, f of x star comma u equals 0, and you're going to solve that for u such that this thing equals 0. Sound good? Questions, thoughts? So this is kind of like one viewpoint on control, which is that like you can think about a dynamical system, this like f of xu thing, as a vector field in the state space. And this u, like you plug a feedback policy in there. What you're really doing, if you think about it, is like you're using your control to like change the vector field and change it into a dynamics that you like, right? That's like one viewpoint on this game. Okay, everyone cool with that? Definitely, yeah. So that idea that you just said is called controllability in general, right? There's a lot of conditions you can impose on F. to sort of say various things about it. So obviously, right, like a trivial example of this is, let's say I gave you a double pendulum, but I only gave, which has 2 degrees of freedom, but I only gave you one actuator. So let's say I only gave you a torque input about the elbow and not the shoulder. Could you do this kind of arbitrary equilibrium point thing in that case? No, right? Because like you've got an equation now where you've got two Q variables that you have to like zero out, right? You only have one input variable to do it. So in that case, you just absolutely can't do this arbitrarily, right? That idea that I just said, where you have fewer actuators than joints or degrees of freedom, that's called being underactuated. And that makes control harder and way more interesting. It means that we have to actually reason about the dynamics in a sophisticated way, and we can't just cancel stuff out arbitrarily. So yeah, this is a big topic. This idea of controllability, it comes up a lot. Okay, other thoughts, questions? Okay, cool. So next topic is we're going to talk about, so now we know what an equilibrium point is. It's a place where the system will, if you put it there, it'll stay there and not move anymore. Big idea. The next topic is is stability of those equilibrium points. So this is also pretty intuitive at a basic level, and we can go back to the kind of the pendulum thing again in a sec. The idea is like the intuitive statement of stability is we're going to ask the question, when will the system, when will we stay near, in some sense, like in the neighborhood of an equilibrium point? Under perturbations. So pendulum example, right? Hanging down, I give it a little whack, it's going to stay in the neighborhood. Up here, let's say I balance it really, really perfectly, and then I blow on it. It's not going to stay there, right? It's going to whip around, and so stable, unstable. So now we're going to kind of take a little bit of a mathematical look at that and figure out how to like think about it and analyze it with some of these tools. So the first thing we're going to do to sort of build some intuition here is look at the simplest possible kind of 1D system. And when I say 1D, I don't mean 1 degree of freedom mechanical system. I mean 1-dimensional state space. So that means, right, X is a scalar. So in this case, these are actually pretty interesting things to think about. So like normally we say, nonlinear systems, there's demons in there, super hard, can't, know too many things about them. Turns out though, for 1-dimensional nonlinear systems, you can know everything about them. It's an interesting, like kind of special case that I think is maybe slightly underappreciated. So in particular, you can write down what's called a phase portrait of these things. So like if I imagine it's only 1 degree or 1-dimensional state, X, I can plot X, and then I can plot X dot on the vertical axis. And this is the dynamics, right? It's X dot equals F of X. This is just plotting F. So I'm going to plot some made up dynamical system that, like, roughly speaking, is something like, X dot equals minus X cubed or something like that, right? Okay, so first question is, where are the equilibrium points of this system? The point at which it crosses the x-axis, right? It's where y equals 0. Right, yeah, cool. So we've got 3 of them in this case, right? Like here, here, and here. Cool. Okay, so next question is, which of these is stable and which of these is unstable? So we're gonna like think a little bit, right? So let's look at the middle one first, kind of the one near the origin, and think about the signs of x dot. So if I start at the origin and I poke it a little bit, push it a little to the right. So what's the sign of x dot in that case? Negative. So that means it's going to go back to the left. Similarly, if I push it a little to the left, what's the sign of x dot? Positive. So it's going to go back to the right. So that middle one has this property that for small perturbations, it's going to end up pushed back towards the origin. I like this shade of green better. Okay, so this guy, you get little perturbations left or right. X dot has opposite sign, it's pushing you back. So this is stable. Let's look at the other ones now. So let's think about maybe the one on the far right. If I push a little to the right, X dot positive, that means it's going to go farther to the right. If I push a little to the left, X dot's negative, it's going to go farther to the left. So this gets red arrows, red bad. This is unstable. For tiny perturbations from that equilibrium point, I'm going to shoot off away from the equilibrium point. And then how about the one on the far left? What do we think? Stable or unstable? If I go a little to the right, X dot's positive, it's going farther away to the right. A little to the left, X dot's negative, it's going farther away to the left, right? So if we draw our little arrows, they're red again. Unstable. Okay, can anyone give me a general statement from this little cartoon picture about the slope of f of x at an equilibrium point and its stability? So yeah, if you want the equilibrium point to be stable, x dot at the equilibrium point must be negative. Make sense? So just look here, right? The middle one's stable, he said. X dot has negative slope. The other two are unstable. X dot has positive slope. Yeah, that makes sense to everybody? So let's write that down. So we got if df dx is negative, stable, and then if df dx is positive, we're unstable. Okay, so one more bonus question. So if I were to, so clearly the middle one's stable, right? And the opposite ones are unstable. What happens if I, so like on either of the outer ones, if I push, let's say we'll take the far right one. If I push a little to the left, where's it going to go? It's going to go towards the middle stable one, right? One on the left, if I push it a little to the right, where's it going to go? The middle stable one, right? Okay. So there's this concept now for a stable equilibrium point called a basin of attraction. It's the set of the state space from which if you start in that region, in that basin of attraction, you're going to end up at the equilibrium point. So what's the basin of attraction for that center stable equilibrium point? Yeah, so everything between the two stable, two outer unstable ones, that entire region is the basin of attraction for the origin in this system. And then everything outside of that is going to blow up to infinity, at least the way we've drawn this, right? Cool. Everyone see that? All right, so maybe I'll like draw that in as a little bonus cartoon. Ah, boo. Why does it keep going to the eraser? Okay. Okay, cool. Now you guys know some dynamical systems theory. Isn't that fun? Okay, so we got this whole scalar thing, right? And we got derive these, yeah. Nope. This is like for this scalar situation, yes, right? Because basically that's the only way it can happen here because you have to have a zero crossing for this to. But yeah, in general, life is very weird and crazy, and nonlinear dynamical systems are really wild. So you've probably heard of like chaos theory, right? There's like all kinds of really, really bizarre stuff that can happen. So yeah, I think you can really only make like these kind of general statements for like planar systems, maybe like two-dimensional systems. There is a statement like the one you've just made that applies to planar systems like 2D state space called the Poincaré-Bendixson theorem that you can check out. It's like basically it tells you there's a limited number of things that can happen in a planar dynamical system, but even just going to a three-dimensional state space, basically arbitrarily wild things can happen. That's where you get like strange attractors and all kinds of very weird chaos phenomena. But yeah, if you're into that idea, go Google, look up on Wikipedia, Poincare-Bendixson theorem. Yeah, this is a deep question, actually. So go check out that Poincare-Bendixson. I'm happy to talk about it offline. But yeah, basically, there's like deep topological things that can happen in higher dimensional settings that can't happen in low dimensional settings. You absolutely can. Yeah. So that would be a flat line, right? I mean, I could draw that, right? So not in 1D, right? I can't have a saddle in 1D. I'd have to at least go to 2D for that to happen. But yeah, what you just said, right, df dx equals 0, that would be, I mean, we can draw it, right? So that would look like this. Say I have a 0 here, and I have something that looks like, you know, this kind of thing, like, right? So I could have like a x squared kind of situation. Yeah. Can you tell me if that's stable or unstable? What's going to happen? If I go to the right, what's going to happen? Unstable pulls up. If I go to the left, what happens? Yeah, so this thing has this weird two-sided behavior, right? So if I go to the right, it's clearly unstable, it's gonna blow up. If I go to the left a little bit, it's gonna kind of come back, right? Which is weird. So there's weird things that happen. So the gist is in the so the thing we just showed is this kind of like slope condition that we're going to talk about it in higher dimensions in a sec. It is a local condition, right? Some very local condition based on basically on a Taylor expansion argument, right? A linearization argument. And in the case where the slope is 0, df dx equals 0, you basically have to do something fancier in terms of analysis. You can't, if it's equal to 0, strictly 0, then basically the message is you have to look at like higher order terms or do something else that's fancier and more nonlinear. And that this linear slope, local slope analysis doesn't hold in the case that it's strictly equal to 0. If you're into that, the stuff to look at is Lyapunov stability. So like Lyapunov stability theory. Happy to talk more about it offline. But yeah, basically you have to do fancier, more nonlinear things in the case where it's equal to 0. And you can't trust this. Yeah. It's a sufficient, not a necessary condition. That's right. Yes, you could have it strictly equal to 0 and still have it be stable. This is very subtle. There are multiple definitions of stability. This one is called exponential or asymptotic stability. They're kind of the same in the setting. There are other notions of stability that are consistent with this, the intuitive definition here of it, like staying in the neighborhood. There's a definition that's slightly tweaked from this one that actually can include the equal 0 case. That's called Lyapunov stable or Lyapunov stability. That one's a little more complicated and involves like some more nonlinear analysis and stuff that we're not going to do in class because we don't need it for what we're doing. But happy to chat about it. And you know, there's more out there. Life is subtle and complicated. This is good enough for most of what we're going to do. Basically, in a control system, if you're designing a control system, you want the strictly less than 0 situation for your system to be stable, if you can help it. Make sense? All right, cool. All right, so we got these conditions. Let's talk about what happens in higher dimensions. So we did this like 1D state space. What do you think happens? How do we generalize this to higher dimensions? So if my state space is Rn and I have a vector space, I mean, have any ideas? So in particular, this df dx thing is now a Jacobian matrix, right? Not a scalar anymore. So what do we do? So yeah, that word is maybe not quite the one we want to use. The idea, but it's spiritually the right answer, I would say. So the idea of negative definite applies only to symmetric matrices, to quadratic forms. This thing is not a quadratic form. It's not a symmetric matrix in general. But the idea there, what's a thing you can say about a negative definite matrix? another characterization of that thing. And yeah, eigenvalues. So that thing has strictly negative eigenvalues, right? And the subtlety here is for a symmetric matrix, the eigenvalues are all pure real. So they're all just negative. In this case, where it's not necessarily symmetric, the eigenvalues can be complex. And so it's okay that they're complex. The condition we want is that the real parts are all strictly negative, right? And physically what that corresponds to is like basically damping. The imaginary parts are oscillatory behavior. So that's fine, it can oscillate. As long as the real parts, which correspond to damping, are strictly negative, those oscillations are getting damped out, then we're good. Okay? Make sense to everybody? And the sort of rigorous argument for why this is the case is that any square matrix, like this df/dx, if it's x dot equals f of x, x dot and x are the same dimension, so df/dx is a square matrix, I can always diagonalize it, right? I can always do an eigen decomposition, and that means I've got some kind of like orthogonal matrix, diagonal matrix of eigenvalues, orthogonal matrix. Orthogonal matrices have like norm one, they just like rotate, they don't stretch or anything. So then everything's in terms of the eigenvalues, right? And so what that's really doing in a dynamical sense is you're basically choosing a set of coordinates such that the dynamics decouple into a whole bunch of individual scalar systems. And then you can just look at each scalar system. And now we're back to the 1D case that we just did. Does that make sense to everybody? So that's like the rigorous argument. Okay, so what we're going to do is take an eigen decomposition. And that is decoupling into n 1D systems. And we already know what a 1D system looks like. So then we've got this condition, the real parts of the eigenvalues of df/dx. By the way, I'm using Julia notation. Eigenvals is the function in Julia that does this. We want these all strictly negative. That means we're stable. And I'll say, right, without getting into subtleties and special cases that we kind of talked a little bit about, otherwise, we're going to just say it's unstable. So basically, if you have any non-negative eigenvalues, we're going to say it's unstable for our purposes. Cool? Everyone got that? Yeah. Yeah. Yeah, so what that corresponds to is they're more damped. So like if they're more negative, farther to the left half plane, it basically means in time, the energy in those modes is gonna get damped out quicker. So it's sort of that kind of corresponds to how fast they'll kind of return to the equilibrium point. Does that make sense? So the subtlety there is like the like actual quantitative values there depend on your choice of coordinates and stuff, right? So if you like use meters versus centimeters or seconds versus minutes or whatever, the actual values of those will change. But the relative values, so if you have the eigen spectrum for the whole system, the relative values like are the same, right? So that's meaningful, and the signs don't change. But yes, you have to be a little careful with like making general statements about that because it is coordinate dependent maybe. But yeah, basically more negative means gets back to the equilibrium point faster in a relative sense. Cool. All right. Everybody good? Okay, so now we're going to go back to everyone's favorite nonlinear system, pendulum again. You got, and this is one where it's, simple enough that we can stomach writing the Jacobian out by hand, maybe. So I'm going to do it once, and then we're going to use auto diffing for the rest of the class pretty much. So this is our dynamics, right? The open loop dynamics with no control input. And if I write down df/dx for this guy, I've got the following thing. Up top, 0, 1, right? Derivative with respect to theta, 0, derivative with respect to theta dot 1. And then the bottom row, I've got derivative of that thing with respect to theta. So that's minus g over L cos theta. And then I've just got a 0 over here. It doesn't depend on theta dot. All right, so that's the Jacobian, 2 by 2, cool. For 2 by 2 matrices, we can actually compute the eigenvalues and really easily, right? A little determinant thing, remember that, maybe. I'm just gonna write them for you, no biggie. So what we're gonna do now is look, we looked at these 2 different equilibria for the pendulum. We got the up, the down. We already kind of know what the answer should be, but we're gonna do the math. So I've got df dx at theta equals pi. That's the up one, right? What do we think? What's going to happen? They're going to be positive. They should be, right? Intuitively. So let's do it. So this looks like if I plug in theta equals pi into our little Jacobian, 0, 1, then we get g over L, plugging in the cosine there. And if I take the eigenvalues of this, I'm going to get plus or minus square root g over L. So one of those is negative, but one's positive. So, right, one's positive, we're done, it's unstable. Okay, now we're going to look at the other one, df dx at theta equals 0. So similar deal, 0, 1. Now we get a sign flip, though, minus g over L over here, and then 0. We're going to do the eigenvalues again. What do we think is going to happen? Yeah, let's see. So here's what actually comes out of this. We get a pair of pure imaginary eigenvalues. So the real part's 0. So yeah, what you got? That's exactly right. So remember, like intuitively from a dynamics perspective, the real parts correspond to damping. So if we have a purely undamped system, that means it's going to oscillate forever. So you have real parts damping, imaginary parts oscillation, right? So it's complex, it's Euler's form, it's complex exponential, right? So the imaginary part, it's sines and cosines. So this is just saying that this thing has undamped oscillations, and the frequency of oscillation is square root g over L, which if you remember your freshman physics, that's the oscillatory period of a pendulum, right? So that all checks out. So this is just saying that this thing's oscillating at that frequency forever with no damping, which intuitively makes sense. But from our stability kind of analysis perspective, this is inconclusive. You cannot say anything about the stability of this system from this analysis. You have to, so it's saying locally it has undamped oscillations in some tiny, tiny neighborhood of the origin. But that means those, if you excite this thing, you're going to excite high order terms in the Taylor expansion. And then you got to worry about those because there's no damping here. So you have to do some other kind of analysis. And this is getting to, if you wanted to rigorously prove that the simple pendulum is stable about this downward hanging equilibrium point, it's not stable in the asymptotic sense, right? It doesn't asymptotically go back to the equilibrium point. It kind of hangs around and does this oscillatory behavior. So that is not asymptotically stable, and that kind of corresponds to this doesn't work. It is stable in this weirder, more general sense, this Lyapunov sense of staying in the neighborhood, in some bounded neighborhood. That's fancier. Go look that up. We can talk about it offline if you want. But from our perspective, if you were trying to control this thing and make it stable, what you would do is add damping with your controller, right? So we can do that. We can say, we can literally use our torque input, our U, to shape the dynamics and basically make it act like there's a damper in there with the controller. So i.e., we can make U equal minus some damping constant KD times theta dot. Just plug that in. And all of a sudden, that'll make us have pure negative real parts. Okay. Any questions about this? So we got linearization. We get equilibrium points. That's where x dot equals 0. Then we've got stable and unstable equilibria. And the way you can check easily is to take the first derivative of dynamics with respect to x, like df dx, which again, remember our linear systems conversation, that corresponds to the A matrix in a linear system. And you can check the eigenvalues out of A matrix. If they all have negative real part, you're stable. If they don't all have negative real part, we're going to just say it's unstable for our purposes. If they have 0 real part, it's a subtle thing and it can go either way, and you have to do something fancier to analyze. And there are fancier analysis tools for this that we could talk about if you care. But for our purposes in the class, don't worry about it. This is all you need to know. Yep.
Do the eigenvalues correspond to specific variables in your state? Like, could you say that it's the thing that the thing that's off that makes it unstable?
Yeah. So yes, there's some interesting stuff to say about this. Remember, we're getting these eigenvalues correspond to particular eigenvectors, right? So yeah, basically what it means is there's a particular eigenvector direction in which the system is unstable. There might be particular eigenvector directions in which it is stable also. The reason this is iffy, right, if you have a mixed spectrum, is that in a real life system, there's like always noise and slight perturbations and errors and whatever. And the deal with an unstable eigenvector, if there's any epsilon amount of excitation in that eigenvector direction, it's going to blow up to infinity, right? So that's why basically if you have any unstable eigenvectors, it's unstable, period, end of story. There are, though, that concept of like having stable and unstable eigenvectors is a very rich and interesting thing to talk about in dynamical systems. There's all kinds of fun stuff there. Like you can actually like compute stable and unstable manifolds around an equilibrium, basically where the system can evolve, all kinds of really fun and cool things. Okay. Anything else? Yeah. I mean, this whole eigenvalue concept is really based on the fact that near an equilibrium point, x dot equals 0, and I can locally approximate the dynamics there by a times x. If you're not at an equilibrium point, that f of x doesn't equal 0. So it's sort of, this doesn't hold up, right? Like basically, if you Taylor expand, you've got the nominal f of x plus a times delta x, blah, blah, blah. And the non-equilibrium setting, that first leading affine term is non-zero. So then this doesn't tell you much, if that makes sense. There are kind of weirder things you can say about stability along trajectories, where the leading term is non-zero, but this is a subtler thing that we're not going to talk about here. Yeah. Oh, yeah, definitely. Yeah, so it's like it does. I mean, you absolutely can physically interpret these things in many cases. I mean, the thing to think about is these are vectors in the state space, not in the configuration space. So it corresponds to, yeah, like you say, some mix of position and velocity and whatnot, right? So it's a little bit subtle, and it depends. I mean, it's a little bit system dependent, but yeah, often you can find nice physical interpretations of these things for a particular system if you like kind of interpret what those eigenvectors are. Okay, everybody good? All right, so thus ends our initial foray into stability of dynamical systems and such. This stuff will come up quite a bit as we continue. So now we're going to switch gears a little bit and start talking about discrete time systems and how to simulate these continuous dynamics in a computer, basically. So let's get into that. Just as a quick, like, motivational thing, in general, right, we can't solve x dot equals f of x for x of t for nonlinear equations, right? Nonlinear dynamics, we can't do it. We pretty much only know how to do this for linear systems and a handful of very, very simple nonlinear systems. Incidentally, the pendulum is one of those systems. Does anyone know that? You can actually exactly solve the nonlinear pendulum. Does anyone know what that solution is? I saw some nods. Where did you hear that from?
I can't remember like where it feels similar to like or ideal orbits where like you can sort of fast forward in time because it's going to follow like a
Yeah, that still doesn't mean you have an analytic exact x of t solution, right? Like that's like, so yeah, but you had a nod too. Do you know what the answer is? This is a weird one. This is a very arcane, like 19th century thing. So it turns out the exact solution of the nonlinear pendulum are these things called Jacobi elliptic functions. Random fun trivia. Like nobody knows this or like teaches this anymore. It's like lost to history. You can Wikipedia that one. It's a fun one. Anyway, okay, so basically the idea is, we need this x of t. We got to be able to simulate stuff and know where it's going to go, right? So what do? We want to represent x of t if we're going to do this in a computer, we can't represent like continuous functions and stuff in a computer very easily. We want to turn this into like a discrete, like set of discrete points, x, like bunch of vectors, x sub k. That's how we do simulation at the end of the day. And the other like fun fact about this is actually there's a sense in which discrete time models are more general or can capture some behaviors that continuous ODEs can't. In particular, I kind of teased this last time, a lot of robotic systems, we have non-smooth behaviors like impacts, right? And those, strictly speaking, are non-differentiable. So if they're non-differentiable, I can't write down x dot, right? There's like discontinuous jumps. Like if I'm really being serious about rigid body assumptions and stuff, if I take a rigid brick and I slam it into the ground and it just stops instantaneously when it hits the ground, the velocity went from minus whatever to 0 at the instant it hit the ground. So what's x dot then? Or, x double dot? Like accelerations are infinite, right? It does weird things. So strictly speaking, you can't simulate impacts and similar things with an ODE sort of situation, without extra hacks and tricks. So that's another reason why this discrete time stuff is very relevant to us. But you can do it in discrete time, right? You just have an instantaneous jump, and that's fine in discrete time. So discrete time models can also capture some effects that continuous ODEs can't, that are very relevant to us in robotics. Okay, cool. So now having said that, here's most of the time we're going to talk about explicit form discrete time dynamics that look like this. So instead of x dot equals f of xu, we're going to have xk plus 1 at some future time step equals f. And we're going to have a little subscript d for this to avoid confusion with the continuous one for today. But like in general, we're just going to do everything in discrete time. So I'm going to drop the little d's after today. Okay, so the little d means discrete. Oh, time are we done? Someone remind me. Start at 12:30. 1:50. Cool. Yeah, just checking. I always mess that up. It's like weird. Did someone have a question? Oh, those are Ks. Yeah, sorry. We're using K for time steps. K will always be time steps. I don't think I'll use any other subscripts. So yeah, this has come up before. Apparently I have bad subscript Ks. I apologize.
Is that also a K on the X of like the top of the screen?
Yes. Yeah. All the little subscripts are Ks or K plus 1s or whatever, and they mean time step. Cool?
Say UK is the control input applied
At time K
time K
to get to xk plus 1. Yeah? Okay. And we'll talk a little bit more about that. Yeah. Apologies if the handwriting is iffy, but yeah, just ask. Okay, cool. So that's explicit discrete time dynamics. And now we're going to talk about the simplest ever discretization that you can do. That is the following: xk plus 1 equals xk plus little time step h times f of xk uk. Right, so it's xk plus 1 equals xk plus little time step times x dot. Make sense? Just taking a little step in that direction. So this little h is the time step. And this whole thing now on the right-hand side is our f sub d, our discrete. And you know what this is called? Yeah, it turns out there's like 3 different versions of Euler, though. So this one is called forward Euler. Yeah. So forward Euler integration is what this is usually called. Okay, simple enough. So now we're going to go do this on our favorite nonlinear system, the pendulum. Everyone loves it. So here we got some Julia. This all gets posted, right, as usual. So just a couple things. This first line is for the Julia package manager. This kind of like generates this like manifest file that actually keeps all the package versions in there. So when I post this, I'll post it with the manifest. And if you run that first line, it's going to make sure you pull in all the exact same package versions that I used. So there should be no versioning issues. This really is important on the homeworks. Make sure you do that so there's no version mismatch weirdness and everything is good. I'm going to import a few packages, linear algebra for obvious reasons. PyPlot is matplotlib from Python, exactly the same interface, same everything. So plotting is easy. Use that. Also has pretty much the same interface as MATLAB's plotting library. So everything's easy there. And then forward diff is the auto diffing, which we're going to use in a sec. Cool. That's self-explanatory. So here I wrote down our continuous time pendulum dynamics with the length and the mass just set to 1. And then gravity is 9.8, what we're used to. The state vector x, I'm pulling out the theta and theta dot. One of the cool things about Julia is you can do LaTeX in it, so I can actually have theta and theta dot, in the code. That's kind of nice. And then this is just me computing theta dot like we did in the notes and spin out x dot, the state vector, right? Everyone cool with that? Really easy. Cool. And then I'm going to write down the forward Euler integrator. This is exactly what we just did, right? So I've got the time step. I'm writing this so it's going to do a simulation run, right? With time step h and final time tf. That's like the duration. And it's just a for loop over this thing. And this is exactly what we just wrote, right? Like xk plus h times f of xk. All good? Questions about that? Okay, so now we're going to go do it. So I'm going to make the time step 0.1. So like 10 hertz, right? Seems fine. And then we're going to simulate for 5 seconds. We're going to see what happens. What happened? It's unstable. That's weird. What's supposed to happen? It's supposed to just oscillate forever, right? Why? Why did this happen? I don't know. Yeah.
Get you a higher like.
So yeah, that's definitely true. Yeah, you had some other thoughts? Something about numerical error? Yeah, that's a good intuition. So we'll draw this out. But yeah, there's definitely like a nice intuition kind of thing where you're basically x dot is the tangent line to like the true solution curve. And you're by taking that tangent and going a little bit along that linear approximation, you're kind of always overshooting the sign. And
dynamics are always right. The dynamics somehow.
it turns out the overshooting always happens. So you'll overshoot on the positive side, you'll also overshoot on the negative side, and that it kind of works both ways. Yeah. So you can do some things. What would you do instead? That's just the time step though. So we can absolutely do that, right? I can make the time step smaller. Let's try. So let's say I do 100 hertz. You could argue, like 10 hertz is too big. Maybe I do 100 hertz. I can't actually see my projector from over here, which is annoying. I have to fix that. Okay, let's do 100 hertz. So that looks better, right? For sure. But if you pay attention carefully, like if I make this 50 seconds instead of 5 seconds and go longer, it's still happening over like a longer time scale, right? So doesn't fix it really. Okay. Any other thoughts on this? Have any other ideas? Yeah. Go. You first. We're not really linearizing anything though. Like we're integrating the ODE. We're doing what's called numerical quadrature. We're approximating an integral. This is really basically the rectangle rule for numerical quadrature. So it's not really, we're not linearizing, right? We're evaluating the nonlinear dynamics, right? We're evaluating f of x. It's all nonlinear. Yeah, you had something too? Yeah, so this is a really good insight. That's kind of what I wanted someone to say something about energy. So you're adding energy to the system here. And what's really going on here is this this numerical integrator, the forward Euler integrator, actually adds energy to the dynamics when you discretize in a weird way. And this is a general property, it turns out. So forward Euler adds energy. Yeah. Yeah. Which is a weird thing, right? So if you have an oscillatory system, it can be any oscillator, it's going to add energy. Which is kind of a weird thing that seems bizarre. Yeah. Yeah, we're gonna get to it in a sec. So I'm gonna now like actually explain what the hell's going on, and sort of we'll get into it. Okay, so let's switch back to the notes. We'll return to this, but hopefully the message is clear. So now what we're gonna do is talk about. So we talked about stability in continuous time. Now we're gonna talk about stability of a discrete time system. Okay, so just as a quick note, right? We had this pendulum sim. And we did, L equals M equals 1. And we did like H equals 0.1 and then like 0.01. You can keep going and it blows up. And that is bad. We don't like that. So you can go try it yourself. The code will get posted. So let's switch it up. Let's talk now about stability of discrete time systems. Okay, so we had the continuous time result, right? We did the negative eigenvalue thing. The way to think about the discrete case is in discrete time, the dynamics, if you want to simulate, say, like n time steps, that looks like function composition. It looks like an iterated map, right? So like x2, so x1 is f of x naught, x2 is f of x naught, x3 is f of x naught, right? So we keep like just iterating the function call, right? A whole bunch. So it's an iterated map. So we've got something like xn equals f, I guess we'll do a little subscript d's, right? F of dot, 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 like f of x naught. How many parentheses? Blah, blah, blah. Okay, so cool. So if I take this thing, we're now going to go do our linearization thing. And it comes down to just doing the chain rule, right? If I just have f of f, and I linearize through that, it just corresponds to a times a times a times a times a, right? Like that kind of thing. So I get, if I take like partial x sub n with respect to x naught, that's really what I'm after here, right? So this is going to turn into df dx evaluated at x naught times df dx, blah, blah, blah. You get the idea, dot, dot, dot. Lots of these chained together. And so what this is coming down to, we're going to write a sub d for discrete time for now. And again, this will go away to the nth power, basically. That makes sense to everybody? Okay, so now knowing a little bit about linear algebra eigenvalues, which clearly you guys do. Oh, and one quick note, we're going to assume we're at an equilibrium point. So we're going to assume that we've also are going to assume that we've changed coordinates or whatever. And like, we're going to assume like we're at x naught equals 0 without loss of generality. Okay, so if this is the situation, right? Yeah. The what? X naught, like the initial x naught, x sub 0. Which, are we talking about this guy? Okay, up here, this is dxn dx naught. So the derivative of like the nth time step state with respect to the initial conditions after I've like run it for a few time steps or n time steps. Does that make sense? And so the idea is if I chain rule through that whole bunch of f's, I'm just going to get, product of those Jacobians, right? So it's like for n time steps, it's going to be just a to the nth power. Cool? No, because I'm assuming we're at an equilibrium point, right? So if I'm at an equilibrium, x dot equals 0. And so if in discrete time, if I'm at an equilibrium point, and I plug that into f, what's xk plus 1? It's going to be the same, right? It doesn't change. It's an identity mapping, right? If it's at an equilibrium point, because x dot 0, we're not moving, blah, blah, blah. You get the idea? So, right. So that's a subtle point. That's a good point to bring up. If I'm at an equilibrium point, then all these arguments are the same, right? I'm at the equilibrium. The output of 1f is the same as the input. So it's all the same, right? Makes sense? So then all these are evaluated at the x naught. Cool. Okay, so now thinking a little bit about eigenvalues and stuff like that. Can anyone tell me what has to be true about that A matrix for this thing to be stable, i.e. to not blow up? Yeah. So yeah, is that, yeah, so complex modulus, magnitude, norm, whatever you want to say. All these things have to be less than 1 inside the unit circle. That's what we're doing in discrete time. So let's write that down. So what's going on here, right? We can derive this. What we're really saying is that in the limit as k goes to infinity, I need a to the kth power, right? That's what we're doing here, times x naught to go to 0. Does that make sense? We're assuming our equilibrium is the origin here, right? But basically what we're saying is that's k time steps of simulation looks like a to the kth power times x naught. This thing's stable. It needs to go back to x naught. It needs to, go to the origin, whatever. So that's kind of what we're looking for as I make k go to infinity, right, for all time. And this has to be true for any x naught for this thing to be stable. It means I'm like going to the origin asymptotically, whatever. And that's what we're saying. So that said, if that has to be true for any x naught, it means it has to be true for the A matrix. So what we're really saying is that this limit as k goes to infinity of just a to the k has to be 0. The matrix itself has to go to 0 in the limit. And that means that the eigenvalues of that matrix all have to be inside the unit circle. They have to have norm less than 1 such that when I do those things to the whatever power to the, it's going to asymptotically go to 0. So yeah, out loud, we say this is inside the unit circle in the complex plane, right? Because we can have complex eigenvalues. Yep. Say again. Yeah, so in general, absolutely. This is so the concept of a basin of attraction is a fundamentally nonlinear concept. So for a linear system, the basin of attraction is like the entire, Rn, the entire state space, if it's stable. So again, this is like a locally linear kind of situation, right? So I'm saying for the linear setting, this is the deal. Yeah. So if I linearize a nonlinear setting system, then this is true in some neighborhood, right? Where basically where the Taylor expansion is, valid or whatever. Any other questions about this? Yeah. Yeah, this is basically the corresponding discrete time version of what we did in continuous time. Yeah, same stuff. So rather than negative real part, it's inside unit circle, but it's basically everything else is the same. That's the only thing to know. Cool. Okay, so now we are going to do this for the pendulum with forward Euler. Which is what we just simulated and we saw was unstable, right? Which is weird. So let's see what's going on there. So remember we have this situation, xk plus 1 equals xk plus hf of xk. That's where this f is the continuous f with the nonlinear pendulum dynamics in it. And so this whole thing on the right-hand side is our discrete dynamics, our F sub D. Okay, cool. So I'm going to now like write this down where we want this A sub D thing, which is partial F D partial X. And this is, if I, kind of look at the thing above, it's I plus H times A, where A is the continuous time Jacobian, right? Just based on what I wrote there. And if I just kind of plug in the stuff from before that we already did, this looks like the following, right? Where this is now the continuous one that we already derived. And I'm not going to like do this by hand because it's annoying, but we'll do it on the computer real quick. And if I like go evaluate the eigenvalues of this guy at theta equals 0 at our downward equilibrium. Remember, in the continuous time case, they're pure imaginary, which in the discrete case would mean exactly on the unit circle, right? Exactly 1. But it turns out they actually come out to be something like 1 plus minus 0.3 blah, 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 I, which is weird. So let's go look at this again in the code. So we're going to actually go do this. So here I implemented what we just said, right? This is that discrete time A. And we're going to check it at that 0.1 time step. So that's what I just said, right? I can do this for, 100 hertz. I can do this, and it gets a little better, but it's still bigger. I can do it for 1,000 hertz. Gets a little better. But here's the real kicker. So what I'm going to do now is I'm going to plot the modulus of these eigenvalues as a function of the time step, h, and look at it as h gets really, really small. So we're going to plot this and see what it looks like. Check that out. So for any non-zero time step, it's always greater than 1. It only approaches 1, aka a sort of like, stable oscillations in the limit as h goes to 0. So basically, no matter how small you make the time step, if you go simulate a simple pendulum with forward Euler, it's going to blow up eventually and be unstable. So if you learn nothing else from my class, never use forward Euler. It's bad for you. It's going to do bad things. It's going to do stupid things and unphysical nonsense. Don't do it. Cool. Any questions about this? Okay, sweet. So let's go write that down. And there's like this intuitive picture that we kind of talked about briefly, which is, we know the exact solution in this case is some kind of oscillatory thing, like a sinusoid, right? It's going to do this kind of thing. This is T, say this is like theta. And what we're doing with Euler is we're kind of like taking x dot, this little tangent vector, right? And what ends up happening here is like, you're always, when you come around these corners, you're always overshooting with that linear approximation, right? I'm always going a little bit along this x dot vector. And so I'm always overshooting the true solution. That's another way I think about this. And that's kind of like how you get this energy blowing up behavior. So a couple of takeaways from this whole conversation. Basically, always be careful when you're doing simulation. Always sanity check on like systems where you know what the answer should be, where you kind of can like sanity check energy or momentum behavior. Never trust a sim at face value. And then, yeah, never use forward Euler for anything real. It is bad. One of my lessons. Okay, cool. So, any questions on that? Forward Euler bad, don't do it. Yeah.
So, with the approximating the data, that explain.
You're approximating the solution curve by taking a small step step along the tangent line.
So the bond is and he's subtracted from the scan. That's so we take the derivative.
No, it's not. Yeah. I mean, yes, trivially, algebraically, you can manipulate that equation in the way you just mentioned, but we're not approximating like we're kind of doing the opposite thing. We're not differentiating, we're integrating. We're computing the integral from like, times k to time k plus h of x dot of t, right? dt. We're computing that integral. And we're approximating that integral with the rectangle rule, right? We're holding x dot constant over the integral and like multiplying by a time step. That's what we're really doing, right? Yes, which we're going to do right now. So hang on there for a sec. So better options. So better explicit integrator is the classic fourth order Runge-Kutta. Who's done this before? Show of hands. Not that many, but yeah, decent number of you. Okay, so this is like the industry standard, that is like uber common. So if you need like the first move, if you need to simulate a smooth set of ODEs, throw it into RK4. It's like the first thing you should do. And the gist is, rather than fitting a line to the solution curve like Euler, this is fitting a cubic polynomial. So it's basically it's fitting cubic splines over the time steps, right? Which is way more accurate than a line and gets you like way better behavior. And takeaway is much better accuracy. And it's a really simple thing you can look up. I guess I'll write the pseudocode for this, and you can find this, many places. So here's xk plus 1 equals f sub d of xk. And we've got the way this works, and I'll show you the code in a sec. You're going to evaluate f of x. You're going to then evaluate f again at the halfway point by taking an Euler step. Then you're going to do it again with another sort of half Euler step. And then you're going to take a full step. So this is sort of seems like it's out of nowhere. It turns out where you get this is by doing quadrature with a cubic spline. This is called Hermite, or is it Simpson's rule or Hermite Simpson or something? It's a classic, like you approximate the interval with a cubic polynomial, and that's how you get these like random coefficients. Yeah.
Does this tend to like overshoot and undershoot equally so it doesn't blow up, or is it kind of like susceptible over longer?
This does really well.
Yeah.
So we're going to do it. So I'll show you. And then yeah, the end result is you basically take a weighted combination of all of these things. And you kind of weight the middle ones heavier. Okay, so let's go do this real quick. Okay, so here's RK4. That's what we just said. I'm not going to derive it. It's kind of a pain, but straightforward. Here's the exact same thing, pendulum, but with RK4. Now we're going to go do the same thing. We're going to do 10 hertz, like what we started with, and plot it. And it looks really good. We can go for a really long time if you want, like let's go for 100 seconds and see what happens. It's really good, right? And if we go check those discrete eigenvalues again, let's see what this, so yeah, see it's like almost 1 to like 5 decimal places. And if we take, slightly smaller time steps, it gets even better. Yeah. Yeah, absolutely. So if I ran it for a really long time in this setting, it would be a little bit damped. artificially, which is kind of wrong, but they're good to lots of decimal places. And we're doing 10 hertz, which is pretty coarse, right? So if I go to like slightly better, like if I did 100 hertz, which is like pretty reasonable, right? It's going to be really, really good. Like imperceptible, right? So like here again, if I did this at 100 hertz, let's say, it's really hard to see. Yeah, check that out. It's like almost a double precision, right? It's like crazy good. So similarly, let's go do that eigenvector plot and like see what it looks like. So check this out. So for small time steps, right over here, it's basically dead on. It's right on one. And then as I increase the time steps, weird stuff happens. So here in this region, it's artificially damped. It's going to lose energy. And if I get the even bigger, it's going to now start adding energy. So weird stuff happens. The message is though, these are too big time steps. You should be doing stuff over here. Yeah. Yeah, pretty much. Yeah. So at that point, you're basically like undersampling the dynamics and bad stuff's going to happen no matter what. Yeah. But yeah, like the message here is this thing's like really solid for like reasonable time steps though, right? Like this is 5 hertz. That's stupidly, big steps, and it's still like pretty solid. So this should be your first go-to move, essentially, if you're going to do simulation. Let's just finish this up real quick. Basically, the message here is the accuracy win from doing this. So obviously, this is more compute, right? This is 4 dynamics calls per time step instead of 1. But the accuracy win far outweighs the additional compute cost. And this is like, you should do this, basically. And the other message, right, is if I do dumb things, like I take way too big time steps. Oh, I forgot to move the code. Yeah, sorry. This will still get messed up, though, if I take way too big time steps. So even a sort of, quote, good integrator can have issues if you do dumb things. So you got to be careful, always sanity check. Okay, and that is time. I wanted to do one last thing, which I'll just tease really briefly. Maybe we'll talk about it next time. This is something called backward Euler. Who's heard of this? A few people. So the only difference is, right, forward Euler, we evaluated f at xk. Here we're going to evaluate f at xk plus 1. So we're evaluating f at the future time, which is weird and like non-causal, and we'll talk about that next time. But just I wanted to show you what happens to the energy behavior. It always undershoots and you get artificial damping. Backward Euler is one of the standard methods used in robot simulators. Like it's what's used by default in Mujoko, Bullet, probably Isaac, although I don't know for sure. All these stock simulators use backward Euler. Why? Basically, this artificial damping is desirable because it means the simulator won't blow up and do stupid looking unphysical things, but it's still wrong. So keep that in mind. Like pretty much all the sims you're running, like Mujoko, etc., they actually have artificial damping added to the simulator to make it such that really unphysical blow up stuff doesn't happen. Okay, that's it for today. See you guys. Catch you next time.